Hello everyone, my name is Paul and my teammates are Aziz, Samir, and Srushti, and we built a university route optimization mapping system for our capstone project.
Our sponsor is our lovely Professor Stephen Knudsen, and the objective of our project is to design and build a system that detects and maps optimal routes between classes taken by University of Alberta students. Our project involved building Bluetooth Low Energy beacon receivers that can be placed in areas on campus to detect the locations of smart devices. We also needed to devise a central processing system, or CPS, to gather the data for analysis. With the data, this system can generate heat maps of an area on campus, and it can also derive optimal routes between locations. We are going to prototype today 3 receivers sending data to the CPS and a web application that shows the heat data derived by the CPS as well as the routes it receives from the CPS after sending a starting and ending point.
This UML deployment diagram outlines the high-level design of our prototype. Here you can see that we have 2 physical entities, our Bluetooth Low Energy Beacon Receivers, or BLEBers for short, and a personal computer that will run our CPS and web app. The BLEBers are what we use to collect data and send it to our CPS, which creates heat map data and routes that can be fetched by our web app. And now Aziz is going to go a little more in depth on the BLEBers and show you how they work.
Okay, so our BLEBers are made of 2 components, as we can see here, one being the ESP32 chip and the other one being the Nordic 52480 dongle. And we went with this dongle because it's low cost and doesn't use that much energy, and it can be portable, as we can see here, using a portable power bank. And it has multiple GPIO pins that are necessary for our UART communication, and it's responsible for running the BLE observer code. And when it comes to the firmware side, it runs a Zephyr OS, and the Zephyr OS allows us to abstract away most of the advertisement packets that are being observed by the Nordic chip, and allows us to kind of focus on the logic instead of going through each communication protocol when it comes to Bluetooth Low Energy. And how we detect these smartphones is throughout each interval, it kind of receives those advertisement packets and filters off depending on manufacturer ID. And those manufacturer IDs can be specific for each company. And we're filtering off specifically for iPhones so that we can isolate smartphones and detect the number of people that are around us. And when it comes to ESP32, as you guys can see, we're using a UART to communicate with the ESP32. And the ESP32, we went with it because it's readily available around the lab, and it comes with an amazing software development kit so that it allows us to rapidly develop. On top of that, for the firmware side, we are using FreeRTOS, and FreeRTOS allows us to have a little bit of run multiple tasks simultaneously. And what we're doing in the ESP32 is we are connecting to the router, our router being a mobile hotspot, and we're setting up a TCP connection with the CPS and receiving those addresses that we're receiving from BLE and sending it over to the CPS. So as we can see here, our BLEBer setup, and with some logging information, we can see that we do have a live connection with the CPS, and all those addresses are being sent.
So the CPS receives data from the BLEBers over TCP, and the CPS is on the receiving end of TCP sockets that the BLEBers are sending messages through. And to handle receiving device data from multiple BLEBers at once, we implemented multi-threading on the CPS so that we could have multiple TCP sockets open at the same time. And each thread would handle one socket, receive the data, and store the data all in parallel. And now I'll just show you a video demonstration of the CPS in action. So right now, I'm running the CPS, and it's receiving messages from all of the different BLEBers right now.
and it's loading all of the messages that it's receiving into a text file over here. And as you can see, this is all the new data that's coming in. So it's getting it each message that's, so yeah, some are coming from sensor 23, 22, sensor 0, and over here is Srushti. She's using the blebber at sensor 0, and Paul is over there. That's his blebber. That is sensor 22. And Aziz is back there. He is connected to sensor 23. So yeah. And this is the data that we are going to use for the trilateration. So every message that's being received has the sensor ID, and then it has the device ID that it's detecting, the RSSI, and the timestamp of the message.
The video you just watched is taken on the second floor of U of A's Natural Resources Engineering Facility, or NREF building. This was where we conducted the experiment for this project. Across this floor, nodes have been assigned to 44 waypoints. These are the red dots that you see on this floor plan of NREF second floor. This whole floor was represented with a graph data structure in our Python server code, which has all these nodes and their coordinates recorded using an AutoCAD scaled model of the floor to capture the actual geographical distances of these nodes in the real world. To track the smartphone devices passing through these nodes, we've estimated that 23 sensors are needed to be deployed on this floor. The positions of the sensors are marked in blue dots on this floor plan. In the same video, Srushti was operating Blabber 0 at the location shown here. Aziz is operating Blabber 23, and Blabber 22 is operated by yours truly. These blabbers form one group out of 17 blabber triads. Each group has node candidates to which a device detected by all three blabbers at the same time frame can be associated. These are the node candidates for this group, and this node is for another group, while these ones are for another group. But why are they grouped in trees, you might ask? Because we are using the trilateration technique to pinpoint the approximate device position using the three known positions of the three blabbers in the same group and the RSSI data sent by each blabber. Let's consider that all blabbers' data for an hour are saved in a text file on the server. Every 5 seconds, there will be an iteration of data processing for all blabber groups. Each iteration can add one heat level to the nodes. Step 1 is the pre-processing of RSSI data to get the average RSSI for each blabber of the same group. Step 2 is converting the average RSSI to distance in meters. The formula used is on the right-hand side where RSSI-P is the average RSSI and RSSI-Kali is the RSSI at 1 meter. We also use basic Kalman filtering to factor the process noise and measurement error into the calculation. Step 3 is performing trilateration, which is done by solving the system of distance equations on the right to get the xy coordinates of the device. Step 4 is determining the closest node candidate to the device using Manhattan distance formula, where x1, y1 is the device coordinates and x2, y2 is the node candidate's coordinates. Once the closest node is determined, the heat level of that node will be increased by 1, which is step 5. These data processing steps will be iterated for 1 hour for all blabber group. After 1 hour, the heat data for that hour will be stored to a JSON file. Here's a screenshot of the JSON file for the heat data. There is heat data for every hour of any day in a specific month. The JSON file can be accessed by the web application via GET request to the server.
Hello, so now we are going to show you our heat data and our routing capabilities in action with the web client that we've created with React. So as you can see here, this is a heat map of the second floor of NREF. And we also have the capability of changing the heat data based off the time of day. As you can see, changing the time changes what the heat map looks like because different times have different traffic. And if you change the day of the week, it also changes. And also we can just show a route to go from point A to point B. So let's say we want to go from room 2118, which is here, to room 220, which is, actually I don't know where it is. Oh, it's right here. Let's see if we can see that route. And it does show us the route to get from the node at 2118 to the node at 20022. We can show another route as well. Let's go from 2001 to 2003. Let's show the route. Oh, well, it's pretty quick to go from 2001 to 2003. They're right next to each other. Let's do a different one to make it a little more interesting. Let's do 2001 to 2118. So yeah, this was just the routing in action and the heat map in action.
Now let's talk about the outcomes of this project. In the development of Blibber system, we were successful in combining the hardware and firmware to collect data. The CPS proceeded by collecting and processing the data from Blibbers, creating heat map and determining the optimum routes. For user interface, a React web application was developed successfully showing the generated routes and heat map of NREF second floor, thus providing an interactive and user-friendly experience. We also faced several obstacles, particularly with transmission of data, as initial effort to have multiple blabbers send data through a single TCP socket to the CPS resulted in inconsistent data flow. Therefore, we implemented a multi-threading to manage separate sockets for each blabber. Additionally, the initial storage plan, which involved using a remote database, was scrapped due to the complexity of making asynchronous calls within a multi-threaded environment, so we decided to have a local text file storage solution. Lastly, time constraint did not allow development of smartphone application. Therefore, we developed a web application that operates on the same server machine, showing the required results. Future improvements for the projects are planned across several key areas to refine and extend its capabilities. The project is aimed at expanding the Blabber network for full campus coverage, ensuring efficient support for navigation. In parallel, there is an emphasis on hardware optimization with the goal to minimize the size and power needs of the Blabbers. The development of mobile application is planned to offer user a more accessible and interactive experience. Recognizing the importance of inclusivity, accessibility feature will be added to cater the needs of individuals with disabilities. Furthermore, the integration of machine learning algorithm is also planned to enhance traffic pattern prediction and improve route recommendations. To improve data processing, the introduction of a data buffering system is planned, which can also streamline database operation. Finally, to ensure the system scalability and performance, database shredding or partitioning is planned considering the significant enhancement of the system's performance. In conclusion, this project integrates Blabbers, a CPS, and a web interface to enhance campus navigation. Overcoming data handling challenges, the multi-threading approach enabled successful result. This project not only improved navigational efficiency but also sets a new standard in smart campus navigation. Future plan for this project includes hardware improvement, a mobile application, and new features, which aims to create a more comprehensive and user focused solution.
We would like to express our deepest gratitude to Dr. Stephen Knudsen, our TAs Eric Halwell and Jingjing Lee for all the help they've given us to make this capstone project possible, and to Intertech for giving us a scholarship for our capstone project.